molecularly absorption of some boundary like CH and HOH, which are consist of overtones and combination bands. So we have a signal which is sometimes overlapping because we have many molecules vibrating at the same time. We know that there are some peaks characteristic of some compounds, but the elaboration is not very straight. It's not like saying, okay, at this wavelength I'm saying sugars and this wavelength I say phenolics. We have to use multivariate approach to deconvolute the signal and having information about internal characteristics. Hyperspectral images is merging conventional imaging with spectroscopy, and what it does, what we have, like when we speak about hyperspectral image, is a stack. We call it hypercubes. And hypercubes is a stack of images, one image for each wavelength. So if our spectral resolution, depending on our spectral resolution, we can have many images, hundreds of images, so one image for each wavelength, and particularly for each pixel, then we are able to have the mean spectrum. So you can work on this mean spectra, pixel by pixel, or you can select your object and extract the mean spectra. You can work on single image because we have pointer. Okay, I'm afraid to use pointer, but we have this hypercube with an image, and if we are interested in single wavelength image, we can work on that. And generally we use also a single image, for instance, to threshold our image and to have our object of interest. Regarding the acquisition, we can go point by point, we can go by line, and by line acquisition is generally useful when you are in conveyor belt, so the conveyor is moving and you acquire line by line. And that's all. So what we can see with these techniques, we can see, of course, what is inside. In the last year, there are many instruments have been developed. They are portable instruments to go on the field. There are instruments, as I said, for online sorting. And if besides a conventional camera, or RGB camera, you add spectral information, you may know what is inside. We know that fruits and vegetables are mainly constituted by water, but after water, the main constituents are sugar and acidity and acids. So this one are for sure the constituent you can see better than others. Water is overlapping a little bit the signals, but we developed a very good model for the prediction of maturity index. So this is our commercial application we can find online, we can find on the market. While latest studies concentrated on the prediction of phytonutrients, and since, as I said, water is the big part of it, and here we are speaking about few milligrams per 100 gram of product, is much more difficult to get the information. But latest study we did, in this study we were able to predict, for instance, phenolics content, antioxidant activity. In this case I'm showing artichokes. This is a work we did on goji berry. Actually, Daniel Fachuraman is my PhD student, just got his PhD. And he came from this university to University of Foggia, and so in his thesis he worked a lot with goji berry. Actually he worked also on many other crops, but the thesis focused on goji berry. And here we can see prediction of ascorbic acid and the total phenolics of goji. This is having this model on the main spectra, so we may know online the content of vitamin in this case, or sugar, we also did, fruit by fruits. And so the color here is a color map, is indicating the concentration of the constituents. But as I said, we have also hyperspectral imaging. Actually, goji berry was already an example of hyperspectral imaging, but you can use hyperspectral imaging in different way. When in that case, in goji, I show you the average value of sugar, for instance, for a single fruit. But we can go inside the fruits, and we know where exactly a constituent is located. If you think to pharmaceutical, you might know very well where a compound is located, and if the process went well, the mixture is okay. But in fruits, we can have concentration map. This is an example rocket leaves. So pixel by pixel, you can have the vitamin C content. This is grapes, phenolics on grapes. You can see different concentration on the berries and on the rachis. This is the distribution of sugars within a slice of fresh cut. This is a fresh cut fennels. I don't know if you are familiar with fennels. I will show you later something. So this is the distribution of sugar. So you can see that sugar are concentrated in the internal part more than on external. So there is a gradient of sugar. And also you see the xylematic vessels. We had a higher concentration of sugars. In addition, we can know something else. So what's going on our product? For instance, we might be able to know about physiological problems. And if we are able to detect physiological problem before it becomes too late, we can make, correction in our post-harvest chain to minimize post-harvest loss. So we can adapt protocols based on this. And when some example of physiological product, for instance, this is chilling injury in eggplants. We stored the eggplants at 2 temperatures, 2 degrees and 12 degrees, and so already after 3 days, we got some, oh, okay, now it seems it's work. It's working, but I don't know where it's, okay, but it's not really visible. Maybe it's too far away. Yeah, maybe it's too far away. That's why. And so we could see the occurrence of chilling injuries already after 3 days, and depending on the algorithm, we could have a good separation of chilled and non-chilled product over time of storage. Still on eggplants, another study. In this study, we did like an ANOVA. It's a simultaneous ANOVA on all the spectrum, so on all the reading on the wavelength, in order to know the significance of the factor, the interaction, and also which wavelength were particularly affected by that factor. So the red one are the wavelength significantly affected by temperature or by time. So we could discriminate fluids stored at different temperature in blue and red in this score plot. And then, so this is the results of the discrimination. Also, we did the other study on green peppers, and we were able to detect also in this case chilling injuries. Another application, a different application, also Daniel helped in this study. He did most of the work. We used fluorescence imaging to discriminate mature green from immature green tomatoes. So when tomatoes are green, it's very hard to see if we can harvest, so they will further ripen when off the plant or not. So in fact, in the pictures after 12 days, 18 degrees, you can see that some tomato did not ripen, and we were able to discriminate so mature green from immature green tomatoes. This is an example of discrimination of common defect in loquat fruits made in cooperation of our group and university and Spain University and Research Center IVIA. The approach was to discriminate first 2 classes, and then so defects and non-defects, internal and external defects, and then all the kind of defects. Sometimes we care about discrimination of particular defects, but what is generally important is that we are able to discriminate defective fluids from not defective fluids. And this is another example from Daniel's thesis, which is about discrimination of three different defects on goji berry, black spot, mold, and visual damage. And particularly for small fruit, it's very useful to have an automatic method to make this selection, because when they are on conveyor belt, doing manually, it will be sometimes impossible. Even if you have a slow speed, maybe the sides on the defects is the other one. And this study, we were able to discriminate sound and defective very well, based on, based on sounds picture. So this, just using the spectra of the sounds tissue closer to the defects, we were able to discriminate sounds and defective fruits. While when we try to discriminate by 4 class, sound, mild, moderate, and severe defects, the discrimination was, of course, a little bit lower. What else we can do? We also used this technique as an authentication tool, as a way to discriminate product according, for instance, to varieties, to time of harvest, but also to cultural practices. And for instance, in this case, I'm showing you the discrimination of 2 cultivars of artichokes. One of these has become in the last years also a protected origin varieties, so we discriminate 100% the two varieties. We also discriminate with a very good performance harvest time for this for artichokes. So we had 7 harvest time and we discriminated very well. This is fennel. I showed you before the distribution map of the sugar. So also in this study, we discriminated among different harvests. And actually, there were 7 harvests, but doing one by one was giving lower performance. But grouping different harvests, like harvest 1, 2, and 3, 4, and 5, 6, 7, could give 94 non-error rates. The same on grapes, we could discriminate 5 harvest time. And this is an interesting work where we discriminated 3 cultural practices, 1 conventional and 2 organic. The organics differed because in the conventionalized, it was let's say a conventional organic system where grower just substitute a chemical with or fertilizer with a allowed one. So it's more similar to conventional, but you use what is allowed by the certification, because we know that organic certification is a wide framework, and you can do many different things inside that. While in the agroecological approach, there was more attention to the organic sources, so they used organic sources for fertilization, also to increase the fertility of the soil. They did these things in the same way, just changing this input, and the discrimination was very high, not only organic to conventional, but also within the 2 kind of organic system. Sorry, I don't know if I said tomato, these were strawberries. I don't know if I did, if I said a different one, because also we did something like this in tomatoes. In these last years, we got this project, which is sustaining low impact practice in horticulture through an undestructive approach to provide, if I can have some water. To provide more information on fresh produce history and quality. So the aim of this project is that we are implementing, agronomists are implementing low input practice, LEAP, we call it LEAP, with a positive impact on the product quality, and we are trying to use a non-destructive tool for quality assessment and discrimination of this cultural practice. So in this way, we think we can support the diffusion of the low impact practice and and also some marketing strategies in order to positively enhance the diffusion of this technique. We applied this on rocket and on tomato. So for instance, here you can see we have two different approach for irrigation, one conventional, so it's time-based, and one sensor-based, which is optimized depending on the needing of the plant, and we have sensor to measure it. Fertilization, we have two levels, low and high, so resulting in for treatment, and you can see the discrimination of the for treatment. We did more or less the same things on tomato, but in this case we used two varieties. One was an autumn-winter cycle, and one was a spring-summer cycles. So over 2 seasons, 2 varieties, and also in one we applied the good water, and in another experiment we had brackish water. So the treatments were 3: open cycle, closed cycle with recirculation, and sensor-based nutrient solution. So in the sensor-based, the nutrient solution was adapted to the need of the plant. In the closed system with the recirculation, for instance, where there was some sensor of water content and also some conductivity sensors. So when for instance, the saline concentration was too high, they recirculated the water. So the water use efficiencies of this system actually depending on the water we use, and so the 2 experiments was different. And because when you use, for instance, saline water, so brackish water, you had a very high recirculation in the closed systems, and so the performance actually were similar to the open cycle. While when we use good water, things were different. In this study also we are trying to predict internal constituents like sugar, pH, acidity, ascorbic acid, and carotenes. And when we did different, the discrimination for each experiment of the 3 classes, and then depending on the similarity on the classes also by group, with sometimes a very good accuracy. But what is interesting is that we measured all the samples in the same data sets, and we classify the tomatoes according to the water use efficiency. So actually, over the 2 experiments, we realized we had 3 different levels, low, medium, and high level of water use efficiency, and merging together the data. We only using, I think they were in green, 16 wavelengths. We could have 90% accuracy in the discrimination. And actually the further studies is now, in addition to discrimination, for rocket leaves, we are doing an experiment with 6 different levels of water use and efficiency, so we can see if we can predict the sustainability of the process. Finally, last part is on shelf life prediction. So for instance, this is an example of quinoa sprouts where, making conventional measurements is very hard because it's a product you cannot manage very well. You cannot put a colorimeter to measure color. And this is just an example of applying 3 oxygen level over time. And also in this case, we did an ASCA, so a simultaneous ANOVA, for the spectral information, and we could see that oxygen was not significant, the storage time was significantly affecting the...
Professor Amadeo, you have 5 more minutes, if you probably can speed up.
See, I'm almost done. This is classification of artichokes by days after cutting, so 0, 2, 5, and 7 days after cutting, and you can see 80 or 87% of on error rate when we measured 0, 2, and higher than 5. Thank you. I show already something on green pepper, and also in this case we can predict the days of storage at 4 degrees. This is the prediction of shelf life for rocket leaf. We did prediction based on the initial quality attributes, so mesophilic, chlorophyll content, and also we did the prediction of the shelf life, so the storability of the product just based on the spectra we got at the beginning, at the time 0, and we actually got a very good prediction model. And as final example, we can use, even on conventional, I will tell you something more about predicting with this method conventionally attributes and shelf life. So we know that shelf life is the result of many changing quality attributes. Sometimes you just focus on the most critical quality attributes which is affecting shelf life, while in this multivariate approach you can use all the quality attributes at the same time. So you can model quality change by, for instance, in this work on lettuce, using a PCA, which is done on all the quality attributes. Then you model the effect of time, because you will see over time that a change on due to the time, so a change of the samples based on time and the variation of main quality attributes. And so this is a conventional approach with different quality attributes of fresh cut lettuce, and we did also the same, just with information of Wisnir spectra. So we had 121 variable fitted by PCN, and then the PC score related to time were fitted with linear kinetics, and we got the prediction of the shelf life, because then you can set up a cutoff criteria and determine the shelf life. So going to conclusion, we know that high quality is a key factor in the vegetable sector, but also that the concept of quality has evolved a lot in the recent decades. Non-destructive quality evaluation are becoming more and more relevant, but further research in this field should be focused on, for instance, simplifying existing method, exploiting the possibility of predicting other phytonutrients, or to apply this model on over a large species or minor crops, for instance. We know that the adoption of sustainable practice can be considered a part of the broader concept of quality. And as I showed you, non-destructive method might be a tool to increase also information on produce history, so on cultural practice, and support then consumer choice. Thanks a lot for the attention. This is our Facebook page.
Okay, thank you very much, Professor Maria Amandio. Sorry for the time, because I need to keep the time very strictly. All right, so if you finish, just have a seat. All right, yeah. And as an additional information, Italy is one of the biggest agricultural producers in Europe, along with France and Spain. So making sure that all the agricultural products are in a good condition is really important. Otherwise, they would have a big loss in agricultural products. Okay, I want to move on to the next speaker, Professor Renato Andrin Filano. Professor Rene, are you there? Are you online now? I need to make sure that Professor Rene is online. All right. Yeah, thank you. Yeah. Before I start, I want to introduce Professor Renato Andrin Filano. Professor Renato Andrin Filano is a professor in economics at the University of New England, Australia. More specific, in business school, Faculty of Science, Agriculture, Business, and Law. His area of expertise are on applied econometrics, agricultural economics, and development. Current research undertakings include the efficiency of productivity analysis in agriculture, education, and local government. He's also actively involved in government-funded research for development projects in Asia and Africa. For the sessions, he will be giving a talk with the topics about understanding from household decision-making to increase productivity through behavioral profiling, insights and implication for intervention design. Professor Rene, are you ready?
I am ready.
All right, if you're ready, I'll pass it to you.
Okay, can you hear me clearly?
Yeah.
Can you hear me clearly?
Yeah, I can hear quite clearly.
All right, okay.
Right.
All right, thank you very much, Mr. Chairman, and good morning, everyone. Selamat pagi, Ibu-Ibu Bapak. For your information, saya orang Pilipin, tetapi tinggal di sini Australia for 32 tahun. I am very happy to be invited to be one of your speakers in this very good conference, and I'm really pleased to be sharing some thoughts to you. I wish I could be there in person, but as you know, travel restrictions still in place. But hopefully at the end of this talk, I would have shared something.
Maybe next time,
for this
Professor.
conference.
Yeah, maybe next time
Right.
we can invite you to come to the country.
Yes, we'll do.
Yeah.
All right. My talk today is actually going to be a little bit of a twist. I'm coming from a social science perspective. And I am going to be talking about some thoughts about understanding technology adoption, especially with the decision-making process of farmers, with the intention of improving productivity. But I will be looking at that from the behavioral lens. My area is basically from a social science perspective, agriculture, economics, and most of the work that I do are actually along these lines. So my focus of the talk is actually looking at this, and one of the main reasons for doing so is because, as we know, there are so many technologies that are being developed that are intended for our smallholder farmers, but the question remains as to why some of these technologies are actually not adopted or well adopted by the end users. So what to expect today? I will provide a brief motivation and introduction, and I will give an example using the work that we do and what I do, and hopefully provide some insights from a behavioral lens in terms of designing interventions. I would like you to join the kangaroo to jump all the way to the conference logo towards the end. So when you can see that, then that means I'm nearly done with my talk. All right. So basically, what we have here is to say that most of you, or like most of you, for example, a lot of us are engaged in many research projects, many research activities, whether it's international or local research for development projects. Most of these projects, I'm pretty sure, are aimed towards improving the productivity or livelihood of smallholder farmers. And central to these undertakings are basically farm-level studies to generate knowledge and information on farmers' needs and identify policy options that would support rapid adoption and diffusion of technologies. What we do here is the core activity is basically we collect data from farmers, we analyze them, we examine their household resources, their perceptions, their adoption patterns, and so on and so forth, using some sort of a combination of a lot of modeling. But despite this being the focus of many studies and literatures in the past, there remains to be a question about, which is actually for us, development practitioners, scientists, and academicians, for us to bring the farmer's perspective into the forefront of our core business, that is technology generation and dissemination. So this is actually where I'm coming from. And also I heard during the opening ceremonies the importance of this conference. And that is precisely so, that there are many reasons why we are undertaking this task. What are the relevance of our activities? First, as we know, population pressure is continuing to increase. And hence the challenge of providing more food in the table, especially in the developing world, will remain a fundamental business for all stakeholders. Second, climate change has brought many challenges that resulted to averting some of the activities or some of the initiatives in order to avert some of the areas that will address these poverty issues. There are many public and private partnerships that have strengthened to increase their productivity, but there remains to be some questions whether these are widely accepted by our key stakeholders. The third issue is the farming systems innovation encompassing new technologies, farm management practices, marketing arrangements are being introduced to many regions to bid in order to increase productivity and of course to improve the livelihood of farmers. Despite these many efforts, as I have indicated in the past, the uptake and impacts of those introduced innovation have been variable and low outside the immediate impact, immediate program areas, even if there are evidence or demonstrated potential benefits to improve productivity, profitability, and farm household incomes. This varying income, this varying adoption or adaptation of innovation are actually common to some of the innovations that have been implemented in the past. One of those examples is the use of integrated crop management. As we all know, the ICM is a holistic approach to sustainable development. The aim of the integrated crop management is basically to enhance the quantity and quality of crop production. This technique of the integrated crop management involves other techniques such as rice cultivation, including integrated nutrient management and integrated pest management. These techniques will improve the efficiency of applying fertilizer, for example, and pesticides and so on. And that also considering some of the human health dimension. There have been some evidence of the success of this technology. However, there are also evidence of disadoption. So I would like to highlight the word that there are some evidence of disadoption, and so therefore we need to consider what that may be the case. Another example in Southeast Asia, case number 2 here, we have an example of a knowledge-intensive management for systems-oriented innovation, such as the Sustainable Resilient Farming System or SRSFI. The Sustainable Farming Systems Innovation actually aims to reduce poverty by making smallholder agriculture more productive, more profitable, and resilient. And the core principle of this innovation is the conservation agriculture-based sustainable intensification. Again, there are evidence of benefits of economically and environmentally potential benefits of this innovation, but there are also varying levels of adoption across the different countries in the Eastern Gangetic Plains, for example. There are also a number of production and market-based innovations in other parts of the world, such as Indonesia or South Africa. This is an area that I'm directly involved. I have a project in Indonesia, of which this is a situation where we have an integrated crop-based livestock production systems. There are innovations, these are innovations that are aimed towards increasing profitability, productivity, and sustainability of the smallholder farmers. And this is based on the existing practices, tools, and technologies that are available to smallholder farmers. And then our main intention is actually to improve the supply of beef by increasing cattle numbers and slaughter way up at the smallholder level. And we have a similar project in South Africa, whereby we have the high value beef partnerships. This is an integrated production and market-based innovations, targeting smallholders with a view of targeting high-end market with free-range beef. Again, these are just some of the many examples of technologies or innovations or practices that we have introduced, that has been introduced to smallholder farmers. Regardless of the context of the innovations of where they are introduced, it is imperative that we understand how these are to be adopted and adapted by our end users. And for this context, I'm using the smallholder farmers as an example. Now, whether it is a production, process, or marketing, or process-based innovation, the success remains a big challenge for us all. The decisions made by farm households are central to the uptake of this particular technologies or farm systems innovations. The adoption and adaptation of new technologies and subsequent performance on smallholder farms will depend critically on the farm management made by farm households. Our farmers, whether they're men and women farmers, they will make decisions on a day-to-day basis that would affect the farm and also the household. So therefore, because they are interlinked, the decisions made about the farm will also affect the household or vice versa. Therefore, an in-depth understanding of the farm household decision-making will allow us to establish a platform for the development of appropriate and relevant and timely intervention. So that's basically our main goal here. In the past, or for several decades, the farm household decision analysis has been the central focus of many empirical studies. And there are varying frameworks that has been considered. And some of those frameworks here are basically including the ones that I have on the slide that actually points into several factors that allows us to consider the drivers of innovation and how it actually affects the main outcome variables such as performance, productivity, poverty or welfare. So as we can see, we have a number of factors to consider, and we have a number of innovations to consider. But despite this evidence, there are still some questions that remains, and some of those questions are already answered or can be answered or has been answered in some of what we know in the literature. The adoption literature, as you know, is massive. There are many, many published papers in the adoption literature. And some of the points that are highlighted in this literature are summarized in what I have in the slides here. This is actually saying that adoption, if we are to analyze adoption process, it is imperative that we should analyze the adoption process. As an economist myself, for example, we assume that the decision-making process is instantaneous. However, adoption is actually a multi-stage process, including awareness, trial evaluation, adoption, revision, or even to this adoption. So it is very much important for us to consider those different stages when we're considering adoption. There has been an emphasis on heterogeneity, meaning there has been an emphasis on understanding the differences between the potential users of technology based on their socioeconomic and biophysical realities, and of course, based on the technology being considered. There has also been an emphasis on learning and the role of social network. Several studies have already described and discussed considering new technology. Well, farmers will start with high degree of uncertainty, but there will take some process of learning. So there's some learning process that would take to reduce that uncertainty. And that would actually be highlighted and emphasize the role of social network and learning in order to avert some of those uncertainty. A diversity of scales and time, there are several studies that have been conducted in many areas of the world in different times. And because these are done in different times in period, there are several conclusions that we could come up with, and they are very much location specific. And one of the other strong focus of the existing literature is actually the strong focus of multidisciplinary nature. Meaning, if we develop the technology, there has been a very much a multi and interdisciplinary effort in order to develop an effective policy framework to enhance adoption, and that will require us a deeper understanding of the science behind this, behind the technologies, and of course, of the other dimensions as institutional or environmental aspects. All right, what are some of the methodological issues about this? We need to emphasize not only about the technology per se being adopted, but examine the nature and characteristics and features of the technology per se. There is a need for us to look at some of the roles of what we could do in terms of the role of social network. And also, we also have to understand the decision-making process of the farmers, going beyond profit. Farmers may decide to adopt a technology, not necessarily because of the profit maximizing behavior, but because of other factors. And of course, it is also important for us to consider, other than just explaining adoption, other just explaining the determinants of adoption, it is imperative for us to be able to predict adoption. By being able to predict production or adoption will allow us to enable to design an appropriate framework, whether it's policy or extension, that will foster adoption by smallholder farmers in the developing world. All right. Despite what we have in the literature, there are still a lot of them that we can still do, and a lot that we can still add in understanding those behavior and decision-making process. When predicting and explaining adoption, we need to consider which matters most are the adopters of the technology. Do we consider the characteristics of the technology versus the adopters? And of course, how do we take into account the sociocultural and behavioral factors? In order to contribute into this, what we are going to look for, what I'm going to demonstrate to you, is the role of behavioral profiling, the role of behavioral and psychological profiling in order to understand some of these intricacies and complexities in the decision-making process. And I would just like to start off with a brief introduction of bridging the gap, the importance of behavioral economics. A classical farm household decision analysis is based on the assumption of economic utility maximization. However, as I've indicated before, there are some failures in the neoclassical economics to fully explain the individual choices that prompted consideration of individual farmers. So one of the approach that can bridge this is to actually use the behavioral economics which would combine multiple disciplines such as social sciences, economics, and psychology through the work of agricultural extension personnel. The behavioral economics will focus broadly on unpacking the black box of human decision-making process and explore the human dimension. So the human cognition in the manner in which tastes and preferences will form and drive the decision-making process. And the intersection of behavioral economics and adoption research will actually provide us insights into farmer behavior that will validate underlying behavioral models or call for improvements in those that are already existing or something that are to be developed. In order to consider behavioral aspects in terms of farm decision-making process, we have some of the themes that we need to consider as far as farmers are concerned. For example, some of the themes, this include but not limited to status quo. This is the tendency of farmers to just make a decision to stick to the status quo or to the default option. When we talk about cognitive bias, it is a systematic deviation from the rational decision-making due to the influence or context of and framing of the information that they received. And of course, we have the decision inertia, loss aversion, the tendency of the decision maker to attach more value to loss than an equal-sized gain. And of course, I have there the social influence, the extent to which the decision maker is influenced by social or cultural factors such as norms that will prevent or may support their decision. And of course, the last one is altruistic behavior. It is the moral practice of looking after the concerns of other human being or environment than oneself. So these are some of the behavioral themes that we can consider in terms of embedding behavioral aspect in understanding decision-making process. One of the approaches that we can do is actually behavioral profiling. And based on this, based on the underlying theories and themes, one of the first steps that we could do is actually to examine the patterns of similarities and differences among farmers. We can use what we call behavioral or psychological profiling. Essentially, this profiling is used in order to design, target, and evaluate intervention or preferred learning style that will enable farmers to improve their performance and increase adoption of technologies, increase adoption of process and tools. and of course, to achieve a broad scale of specifically designed interventions that are targeted towards the smallholder farmers. Now, it is another reasons why it is important to conduct profile of farmers. It is important for us to identify the key behaviors that are important and bottleneck in disseminating the technologies. As we know, we can understand through behavioral profiling, reducing or eliminating destructive behaviors. It
Professor
will promote.
Rene, Professor Rene, you
Yes?
have 5 more minutes.
Yes, that's all right.
Yeah.
And then basically, some of this are basically can be considered in terms of behavioral profiling. The behavioral profiling is governed by a lot of theories in behavior, as I said here, on attitudes and social norms, behavioral control, and self-efficacy. Those are the themes. And this is actually governed by the behavioral wheels, of which it is actually divided into 3 areas of a dimension. The green is measuring about the capability of farmers and motivation and the opportunity. The red one would reflect the intervention functions, and the outer one will reflect the policy categories or intervention, or including communications. I would like to provide an example of this behavioral profiling into 2 contexts. Based on the example that I had mentioned, the Farm Behavior Project in Bangladesh, of which we have interviewed 746 farmers, and also in South Africa, where we interviewed 435 farmers. Again, the main objective of this is to basically obtain behavioral profile of farmers so that we can identify appropriate intervention. What have we done? So in order to do this, we've used a behavioral science-informed instrument to interview farmers based on the theories, based on the things that I have indicated. We've used multivariate and latent profile analysis in order to summarize the data that combine the behavioral profiles that allow us to examine the patterns of similarity and differences. The behavioral profiling instruments includes the following dimensions, as I have already flagged when I mentioned a while ago about the different behavioral themes. Some of the results that we have based on our behavioral profiling, this is the context of Bangladesh in terms of adoption of system conservation agriculture. We're basically able to group farmers according to behavioral aspects. And in this case, if I may just take you through to some of the things that of the variables here, these are considering the self-efficacy and so on. And as we can see, there are 3 distinct groups that we have here: Profile 1, Profile 2, and Profile 3. So Profile 1, who are these farmers? Basically, these are the ones that are majority of the farmers, they are the ones who are low in everything. However, they're continuing to understand and continue to seek information about the benefits of the technology. And profile number 2, these are the those that are in between. They believe that they have the capability to do things, but they are precluded from having not having some social support, so therefore they can adopt the technology. And of course, profile number 3, those are the innovators, positive-minded. They are all positive in everything. They have so strong social support. So as we can see, we are able to disentangle and be able to classify farmers accordingly. How about in South Africa? We also have 3 distinct features or group of farmers according to their behavior. The ones that we have in South Africa focus mostly on personality of farmers, being open, being conscious, and agreeableness. Those are some of the things that we consider. And we've separated the things for farmers, poultry and livestock farmers in beef, and we have 3 distinct information also. And of course, similar interpretation as what I have in the previous context as in Bangladesh, which means profile number 3 are the ones who are confident about their ability to succeed. They are the innovators. They are the ones who are open to innovations. So what are the implications for intervention here? Of course, persuasion, the messaging. How do we package the framing of our messages to farmers? Some of the examples of the intervention could be nudging. We could probably provide incentives through micro-incentives or pre-commitment. The role of social proof and education and training are imperative in advancing and accelerating the adoption of technology. When we are designing intervention, it's important, what are we targeting? Are we targeting the physical capability, psychological or physical opportunity? So those are the things that we need to consider when we design intervention. And intervention should have all the key characteristics such as affordability, practicability, effectiveness, acceptability, side effects, and equity for all sector or appease. And finally, some of the things that we need to consider based on the behavioral profiling, we are able to have increased knowledge and understanding about the benefits of our technology. It can be done through education and training. We can examine and evaluate the role of information or communication to improve the positive mindsets of our farmers. And of course, providing example to farmers to emulate and aspire are paramount. And finally, the role of social support and social capital and collective efficacy are very much an important consideration when promoting technology to our smallholder farmers. The main question and the main challenge for all of us is, where is the best venue for doing this? Now that is actually what I wanted to say and what I wanted to share. And if you have any question, I'm more than happy to ask during the Q&A.
Thank you very much, Professor Rene Villano, for the interesting talk. And to be honest, it is really new for me as a person from non-economic backgrounds, but it is really interesting. Some of you might be aware that we cover a wide range of topics for this talk today, from technology to economic. This is because we want to make sure that sustainability is not only in the technological level, but should also in economic level, in community level. Because you know that there is no point if the technology is there, but the readiness of the society isn't. So we need to prepare both of them at the same time. So for the next one, we have a Q&A session. If you have any questions, please raise your hand. Either you are online or you are in here, you are free to. All right, so there are two participants. Want to be the first? All right, Professor Hendrawan.
Okay, thank you very much for the opportunity. I would like to ask to Professor Amudio, because I think this interesting topic and it's related to my research. I just want to ask about hyperspectral imaging sensor. Yeah, so is it possible to implement this technology in the pre-harvest system? Because most of your research is about post-harvest system. In pre-harvest system, we can monitor, for example, like fruits. Oh, this phenolic content is already rich, or this vitamin C is already maximum or optimum already, and then it's time for harvesting. Okay, so it is possible to implement the technology in the real situation in the greenhouse or something like that, and is it feasible? Because I think the technology is a little bit expensive for implementing the hyperspectral imaging. And then the second question is about the accuracy. I read the accuracy is 84 or 89% or something like that. Do you have any experience to use other classifier rather than the PLSDA? Because I think there is two main factors that affecting the accuracy: the sensing device and also the classifier method. So have you ever made any experience for research about the using the classifiers methods? Thank you very much.
Okay, thank you very much, Prof. Yusuf Hendrawan. Any more question? One more question, if any?
One by one.
One by one. All right. So yeah, Professor Maria Amudio.
Thank you. Thanks for the question also. Yes, you can use it on pre-harvest, and we are actually involved in many projects also now, focusing on this. It's true, it's expensive, but actually there are some devices that are becoming cheaper. And actually, for instance, we are involved in a project where University of Milan is developing a small hyperspectral portable system with 3D printing, a very low technologies. So we will try to build this, and it will be very cheap. Of course, if you can reduce the numbers of wavelengths, if you don't need the full spectra, this will make it cheaper and simplest also for modeling. In that case, you will have this technology ready. About also accuracy, okay, we are also now, and actually another project we will start is about having a tools on a robot for machine harvesting. For instance, we will test it on grapes. And yes, when you move to, let's say, field condition, maybe PLS is not the best tool while we are trying machine learning algorithm. And actually, we are now making a comparison of the performance, but looks like they work very well. And of course, the implementation will be easiest. When you speak about accuracy, also you have to remember that accuracy is also related to reference methods and to the attributes you are measuring, and also to the error and the variability of this parameter in your fluids. And we know we have a lot of biological variance. For some measurements, if you do the same on the same sample 3 times the measurements, you have some already laboratory error. So of course, non-destructive measurements cannot be better than the conventional one. If you already have an error, we can accept a 10 to 20% difference. And also keep in mind that, of course, if we are predicting vitamin C, we are very happy if it's already 80%, because you will skip many chemicals. Of course, you need higher accuracy to decide the time of harvest, so based on physiological maturity and sugars content in this phase. You need higher accuracy. But I believe that if we are able to give information on nutritional content, even if the accuracy is not very high, it's still a huge contribution. Useful information you can add to the conventional one. So we need higher accuracy to decide time of harvest. And then if we can give some indication the nutritional content, why not? Even if the accuracy is not so high, you have to consider we are really predicting small amounts. So I remember when asking for equipment, the company was saying, no, you cannot use them to predict. So they didn't want to sell me, because they say, then you will tell me it's not working. Give it to me, let me try at least. So I guess there is something still to do, I mean, for these things, but we might have some results soon. Thank you.
Okay, hopefully it answered the question. Is that? If you probably have any more questions, probably you can have more discussion after the talk. Right, so this is Professor Yusuf Hendrawan. His expertise is in precision agriculture, so you probably can have a great talk after this. Okay, is there any more question in this room? If there is no more question, I will move on to the question online.
There was
Okay, I want to read the question online to Professor Rene. Professor Rene, are you there?
I'm here.
All right, yeah. So I'll read the question. Sorry, I need to move a bit. And the question is, to profiling farmers, do we have to get along with them to understand the behavior? Can we understand them by doing FGD or focus group discussion with selected respondents? And how have you done this to the fishermen as well? Fishermen. Okay.
Can you repeat that, please?
Do you get the question? No. Should I read the question again?
Yes, please.
All right, yeah. So I need to read very carefully. To profiling farmers, do we have to get along with them to understand their behavior? Can we understand them by doing FGD, I mean focus group discussion with selected respondents only? And have you done this approach to fishermen?
Okay, thank you very much for that question. Okay, when there are several ways of how we could do profiling, and one of the one that you have mentioned is actually to be working with farmers directly. One thing that I forgot to mention is that when we design the behavioral science informed instrument, those instruments or those questions that we use in profiling was actually designed on the basis of the initial results that we have from FGDs and key informants. And so what we did first was to actually do a key informant focus group discussion, and we basically look at some of the key elements of decision-making process, and we embedded the theory and the themes to design a behavioral informed instrument. And then when we do that, we have selected farmers in order to implement a series of questions. There are many, many questions that are trying to measure the different aspects of behavioral themes, from theory of plant behavioral all the way to theory of, from the social identity theory. So to answer your questions, yes, some of the ones that you have mentioned are actually applicable in terms of profiling. But what we have done is to actually be able to identify the groups, because once we have identified the profile, we can then move forward and do post-analysis. Understand who are those farmers, what are they doing, what are their circumstances, where do they live, and so on and so forth. Yeah.
Okay, is that all? Okay, I hope they answered the question. And we have one more question online, if there is no question from this room. All right, from Pak Bambang.
Thank you, Pak Wahyu. My question for Professor Amudyo. The undistracted quality evaluation is high technology. And it is not easy to apply in farmer level or in industry. Could you tell us, please, how to transform from laboratory to farmer or industry level, especially in your country or in your university? Thank you. Yeah.
All right, so did you get the question?
Just last part. Can you tell us how?
Yeah, if probably I can explain it. So, so far the technology is in Indonesia. So far the technology is like in lab only, but it's not applied in industry or to farmers. What about in Italy? Is it applied in farmers already or in industry? And what's your experience about that?
I think at the industry level is more applied than on farm level, because they already have some machine vision system, as I said. So to add a detector is much easier for that, or to change camera, and it's much easier. So as I said, for sorting and grading, they are used. At farm level is a little bit, yes, more complicated. But of course, for doing this, you need remote assistance, for instance, in the first part. We have technology which can be guided online a little bit. You can hide the users, but and also the software should be very friendly. So to develop friendly-based system, you don't have to make any elaboration by yourself. It's the software that should give you the answer, and in the simplest way. So the work to be done is on this, to make it friendly. Because, for instance, if you think to the prediction, which is applied for food. I mean, other kinds of food. You do the reading and you have the values in your screen. So you have to do something like that, or you have to say ripe, unripe, and so you can make the easy, friendly tools for people to use, but of course you have to give them a package already working, and this is what we are doing. They don't have to make any decision. I think once the model is set up and you have a company for transfer, and we are working with companies to make this technology transfer, the use should be very, very easy.
Right, so can I say that until now there is no application in farmers level, but it's already applied industrially?
Yeah, I think
right.
so. This is the most used part.
Okay, I hope that answered the question. Okay, I have one question.
You know, sorry, at farm level, you also can use now drones, and so there is remote sensing. I mean, how do you say? You can do it on the fruit, so you can try also from remote sensing to have some information about, for instance, the maturity levels of the crop. This is also the further step. And there are some applications, more on water status, other things. There are, I think, some company already using, and we might also work on this.
All right, so yeah, it isn't applied in farmers level, but you start to apply in the farmers level. You start to apply in the farmers level at the moment. So it's not widely applied in farmers at the moment. So that's, I think, the answer. Okay, I have one more question, and we have to stick to the time. The question online is from Diding. The question is to Prof. Amudio. You mentioned several approaches to authenticate quality and exchange of several specialty products in Italy. Please give your opinion about the data fusion approach by using several sensors on the same time to monitor our food quality. So the question is about how we going to do the fusion of the data from several sensors.
Of course, we might do this. For instance, visible or digital imaging and hyperspectral, or even you can add more sensor. Of course, the more sensor you apply, the more complicated it is.
Sure,
yes, this is another way to reach the objective, to have some other sensor, but I would stay on non-destructive sensor because this is the best way. Yes, we didn't work on this, but
it is possible,
I think it's
but
possible.
More complicated.
Yes, it is possible. You have to scale up everything and to merge information, which is something. For instance, in this project on automatic harvest and robot machine, so we have these intelligent systems, and we will, I don't know if we will merge the sensor, but we will have visible digital imaging and hyperspectral imaging in the Visnir. Hopefully, I mean, we can see if we have to merge information or if we can use just hyperspectral or just digital, depending on the sort, but the decision is to harvest or not to harvest. And then there are other DS, decision support system, based on other sensors to decide if to make other agricultural operation like fertilization or other defense things. We will see if to merge this information or not.
Yeah.
But this is another way. This is an option, I mean.
Yeah, technically it is possible to do fusion of data from multiple sensors, but it will be more complicated if we're doing that. Okay, sorry for the time, so we run out of the time. So this is the end of this session, and thank you very much for Professor Maria Amudio and Professor Rene Villano from New England, Australia. And thank you very much as well for all participants. Thank you.
Thanks again.
Thank you very much.
for inviting me.
Thank you, Dr. Nugraha, for moderating this session. We'll now start with the second plenary session. For the second plenary session, it will be led by Dr. Muhammad Nurholis. Dr. Muhammad Nurholis is a lecturer at the Department of Agricultural Product Technology, Faculty of Agricultural Technology, Universitas Brawijaya. He was graduated from Yamaguchi University with a doctorate degree in 2019, and his field of study is biotechnology. Without further ado, let us welcome Dr. Nurholis. Dr. Nurholis, this stage is yours.
Good morning, everyone. Can you hear my voice? Is it clear enough? How about in Zoom? Can you hear my voice? Okay? Okay. In the second session, we have 3 keynote speakers. The first speaker is Professor Babang Dwi Argo from Universitas Brawijaya. And second speaker is Professor Mamoru Yamada from Yamaguchi University. And the third speaker is Dr. Mingming Zhu from Cranfield University, United Kingdom. Okay, let's go to the first speakers. The first speaker is Professor Bambang Dwi Argo. Professor Bambang Dwi Argo graduated from Agricultural Engineering, Bogor Agricultural Institute, Indonesia. And then he continued his master degree in energy system engineering, University de Perpignan, France. I'm sorry if I mistake, Prof. Bambang. And then he obtained his PhD degree in energy system engineering in Toulouse, French. Okay, he has expertise in the design of agri-industrial tools and machines, mainly related to their functional and structural design. Supercritical reactor used for the management of biodiesel without catalyst. He published around 39 scientific papers indexed by Scopus with each index of 5. Okay, to shortcut we can continue to Professor Bambang Dwi Argo to deliver his talk. You have 30 minutes, Professor.
Assalamualaikum warahmatullahi wabarakatuh. Selamat siang. Good morning. Dear participant, first of all, I would like to thank to the seminar organizer and Prof. Imam as the Dean of the Faculty of Agricultural Technology. Invite me to one of the speaker in today's seminar. Okay. In this presentation, I'm going to deliver this presentation with the title Advance in Supercritical Technology Extraction. Okay. This title related to the increasing demand for food, medicine, pharmacy, and cosmetic product. Okay. dear participants, this presentation content include the first about the supercritical fluid in general, and the second, the application of the supercritical fluid, and the third, the experience of planning, building, and testing supercritical reactors, and the fourth is the prospect of semi-continuous supercritical reactors. Okay. In discussing supercritical fluid, the thermophysical properties on fluid are important information, and these properties are presented in the first diagram as in this figure. Supercritical fluid is any substance at a temperature and pressure above its critical points. Yeah. Commonly used supercritical fluid are CO2 and water. In the first diagram, there are four phases, namely solid, and then gas, and the liquid, and the supercritical region. In the supercritical phase, a fluid can be in the form of a liquid or gas, so without any boundaries. And this condition is important information about supercritical fluid. Okay. Dear participants, in the following table, we can see some example of solvent along with the value of molecular weight, critical temperature, critical pressure, and critical density. From this table, we can see that critical temperature of the solvent varies greatly. Methane is the lowest, for example, and water is the highest for the critical temperature. I would like to show the physical properties of supercritical fluid. In this slide, you can see many physical properties of the supercritical fluid. Excuse me. And I would like to show the physical properties of the supercritical fluid, which can help in many processes, such as extraction and synthesis of nanoparticle, and also biodiesel production. Okay, excuse me. The following, we are going to present some application of the supercritical fluid. This figure shows the, that the supercritical fluid can be used for various processes. And in this presentation, we will discuss several use as are widely used in bioprocess technique, such as extraction, nanoparticle synthesis, micronization, and then the synthesis of biodiesel. Okay. From the supercritical fluid properties, we can use it to extract certain component from the product, especially biomass product. The basic procedure for extraction with supercritical fluid is follow. The first is the partition of volatile substance by contacting supercritical fluid with fixed material. Second, soluble material dissolved into the supercritical fluid. And then the extracted component then separated by changing pressure and temperature. And finally, the supercritical fluid recompressed and recycled. And then from this process, yeah, the solvent as supercritical fluid can be reused and will be not disturb the environment, and it is efficient in the use of the material. This. The following figure show the extraction process, yeah, using supercritical fluid, and then the essential part consists of extractor and then separator. Yeah. We use CO2 tank. Yeah. We supercritical fluid, we use CO2, and then this is a general scheme of the system of supercritical extraction. And we also see here, yeah, supercritical fluid extraction has several advantages. Yeah. It is relatively rapid for low viscosity and high diffusivity of Icgab, easily recoverable by changing pressure and temperature, and the non-toxic solvent leave no harmful residue, can be selective by controlling density, and then the last advantage, high boiling components are extracted at relatively low temperature. And then it can be used for the extraction of several types of products, such as food and flavoring industry, yeah, for decaffeification of tea and coffee, yeah, extraction of essential oil, aroma material from spices, etc. This is and we can see here, yeah, there are several extra products using supercritical fluid extraction that have been marketed with health benefit and high economic value, such as the essential oil of lavender, essential of ginger, and essential oil of basil. Okay. Ladies and gentlemen, in this table, we can see some result of essential oil produced using supercritical fluid extraction. Yeah. Roasted peanut need CO2 as a solvent on temperature equal to 50 and pressure equal 9.6 megapascal as optimal process condition. And the other material also need specific optimal condition like Macuna, Aterima, Cafe. So from the table, this table, we can make conclusion that in the research of supercritical fluid, to determine the optimal process for every material. Okay. Also, there are many research. Yeah, supercritical fluid extraction can also be used to reduce fat content. For example, for cheddar and Parmesan cheese, yeah, we can minimize the fat until 51%. And then for flat flavor from sticky rice, yeah, pandan leaf for pharmaceutical material, ginger to pharmaceutical material, and black pepper use it for medicine material. And the other one, we can also for aromatherapy, yeah, Eucalyptus globulus, yeah, leaf of the Eucalyptus globulus for aromatherapy, and then lavender also for aromatherapy. Okay. The second application of supercritical fluid is used to form nano-sized particle. There are several records for the formation of nanoparticle as follows. Yeah. The first is supercritical fluid precipitation technology produce a particle with nano dimension. Yeah. Supercritical fluid provide a number of ways of achieving this by rapidly exceeding the saturation point of solute by dilution, depressurization, or combination of these. The third, this process occurs faster in supercritical fluid than in liquid, promoting nucleation of crystal growth and yielding very small and regularly sized particles. And then recent supercritical fluid have shown the capability to reduce particles up to a range of 5 until 2000 nanometer. And this technique is largely used in pharmaceutical industry. We are going to micronization. Yeah. This is a supercritical fluid micronization is one of the modern technologies. Yeah. And there are three kinds of technology to produce micro-scale products. Yeah. We can give name RES, yeah. Rapid expansor supercritical solution, and then SAS, supercritical anti-solvent, and PGSS, particle from gas saturated solution. RES method. Yeah. The explanation of the RES method is as follows. The SGF is used to dissolve the solid material under high pressure and temperature, thus forming a homogeneous supercritical base. The second, the solution is expanded through a nozzle and small particles are formed. And then, at the rapid expansion point, right, at the opening of the nozzle, there is a sudden pressure drop that forces the dissolved material to precipitate out of the solution. This is important information. And the last, the crystals that are instantly formed enclose a small amount of the solvent that, due to the expansion, change from supercritical fluid to its normal state, usually gas, yeah, thus breaking the crystal from inside out. At the same time, for the reduction of size, chip, while the forming and breaking crystal collide with each other at the vicinity of the nozzle. The particles that are formed this way have a diameter of few hundred nanometer. And we can see here the instrument for RES method. Yeah. We use SGF, CO2, and then we also need a fluid reservoir, and the last one is the RES chamber. Yeah. We have a nozzle here, so the expansion nozzle can create the micrometer of a particle. Okay. The SAS method is the second type of the micronization method. In the SAS method, the solid material is dissolved in an organic solvent, and a supercritical fluid is then also forced by means of pressure to dissolve in the system. In this way, the volume of the system is expanded, thus lowering the density and therefore also the solubility of the material of interest is decreased. Yeah. This is important information. As a result, material precipitates out of the solution as a solid with a very small particle diameter. This is a explanation of the SAS method. And for laboratory scale, we can use this scheme. Start from number 1 until number 90. All of the components in the rest method. Okay. No? Okay. Okay. The following scheme is used to produce micro-scale product using the PGSS method. The system consists expander, and then nozzle, autoclave, cyclone, electrical filter, electrical motor, and vacuum form. Okay. Yeah. You know that VGSS method is the third type of micronization method. Yeah. In all three methods, describe the effect that causes the small diameter of the solid particle is the supersaturation that occur at the time of the particle formation. So here the this information is important when you will design the PGSS method. And then the PGSS method has the advantage that because of the supercritical fluid, yes, the melting point of the solid material is reduced. Yeah. Therefore, the solid melt at a lower temperature than the normal melting temperature at ambient pressure. This is also important information when you will design a PGSS method. And then this process also don't demand long processing time like the case in the traditional method. So we can develop this method by using this information. The last supercritical fluid here by diesel production. Biodiesel production can be divided into two methods. The first method is using a catalyst, and the second method is without catalyst. Conversion of vegetable oil to biodiesel is via trans-esterification reaction, where the triglyceride is converted to the methyl ester plus glycerol. This is usually done using methanol and caustic or acid catalyst, but can be achieved using supercritical methanol without catalyst. This has the advantage of allowing a greater range and water content of feedstock, in particular used cooking oil. The product does not need to be washed to remove catalyst, and it's easier to design as continuous process. Okay. Next, I will present our experience of designing, building, and testing supercritical method for production of biodiesel. Here we I will show the research experience in the designing, manufacturing, and testing of batch type supercritical reactor for production biodiesel. Yeah. This is sorry. Okay. The specification of our supercritical reactor, the volume is 1,000 millimeter. In Japan, until now, 50 millimeter, still small. Maximum pressure until 220 atmosphere. Maximum temperature until equal to 300 degrees Celsius. We design in batch type, and then the component is the reactor tube, heater, one-way valve, control system, expander, piping system, frame extra. We use material SS 316, and we also control the system by automatically for temperature and pressure.
Professor, sorry, you have 5 minutes left.
5 minutes.
5
Okay.
minutes.
Yeah. This is a component of the critical reactor. Okay. There are 15 parts. This is a tube. Before we fabricated this system, we have simulated about the stress profile of on reactor tube. This is, and after that, we in these tables show the result of oil hydrolysis using a supercritical reactor. Oil hydrolysis test was carried out using 2 factors. The first factor is the variation of the ratio of oil and water, while the second factor is process time. The response variable observed was the volume of free fatty acid, and maximum hydrolysis takes place at ratio 95% oil and 5% water, and then hydrolysis efficiency range from the 50 until 96.4%, and temperature and pressure usage are 270 and 220 bar respectively. And we also have the result. The following tables show the result of the esterification using a batch supercritical reactor. Free fatty acid resulting from hydrolysis is esterified under supercritical condition to produce biodiesel and glycerol. In the esterification process, the ratio FA and methanol is 71% compared to 21%. And then the esterification process was carried out at the pressure 220 bar and the temperature of 270 degrees Celsius. And the maximum esterification efficiency obtained is 98%. Okay. We also calculate the total energy requirement for hydrolysis and esterification, and the result like in this table. For treatment number 1, we can see here the total energy requirement is 127,305 kilocalorie. It's still high, it's still very high, because we use the batch supercritical fluid. And all of the result for this testing, process temperature, and then process pressure, process time, ratio of water and oil, ratio FAA and methanol, pump result, and then energy use efficiency. The last one, I would like to development of semi-continuous supercritical reactor. Yeah. I would here, yeah. Excuse me. Okay. The problem is how to conduct or how to perform heat exchanger at high pressure and temperature. So we have an idea to create a heat exchanger divided in the closure part. Yeah. Here in the we have sorry. Oh, it's finished. No?
Is it already finished?
Okay.
Huh?
Okay.
Sorry, Professor Bambang
It's
Duargo,
finished.
because we have a limited time for this session. We have 3 speakers, so I would like to say very sorry for I stopped your presentation. Okay, let's move to the second presentations. I would like to say hello to the keynote speakers in Zoom. Are you there, Professor Yamada? Hello, Professor Mamoru Yamada. We have 2 speakers through Zoom meeting. Hello, Professor Mamoru. Are you there? Okay. Hello. I couldn't hear the voice.
Hello.
Okay. How are you?
I'm fine, but the mute is not clear easily.
Okay.
But now I think okay. I try to share. It's okay?
Okay, I would like to read your curriculum vitae first.
Okay.
Professor Mamoru Yamada is Director of Research Center for Thermotolerant Microbial Resources in Yamaguchi University, Japan. He's a graduate from Agricultural Chemistry, Yamaguchi University, and continued his master's degree in same university in Japan. And finally, he obtained his PhD in Biochemistry, Yamaguchi University, Japan. His expertise is study about respiratory chain, gene expression regulation at stationary phase, mechanism of thermotolerance and high temperature ethanol fermentation in bacteria or yeast. He published more than 148 scientific papers indexed by Scopus, which each are indexed 34. So, Professor Mamoru Yamada, please deliver your talk. You have 30 minutes from now.
So can I share at the not working? Oh, okay. Okay.
Yeah, please share your presentation, Professor. Can you share? Okay. That's good. Okay.
Okay. Thank you very much. First of all, I would like to express my sincere gratitude to the organizing committee of the 6th Icgab to offer this opportunity of keynote. My talk, the title is Potential of Thermotolerant Yeast and its Application for High Temperature Ethanol Fermentation. This high temperature means around the 40 degrees Celsius. But if you use Saccharomyces cerevisiae, the temperature should be kept around 30 degrees Celsius. So about 10 degree higher temperature fermentation. Over 20 years, we organized 3 international core programs with Asian countries focusing on tropical microbes and their application. In these core programs, there are 250 researchers from the 70 university and 7 countries, and including the Indonesian scientists. In these programs, University of Brasilia was a core university. As you know, global warming is a worldwide issues of this century. We believe that the application of tropical microbes can contribute to solving some issues related to SDGs. We can apply some tolerant microbes for fermentation and biodegradation, bioremediation due to its the resistant to heat and the many stresses. Especially the high temperature fermentation has several merit. That is reductions of cooling cost and prevention of contamination and saving hydrolysis enzyme cost and the easy operation. The Samatoran yeast in this topic is Culebromyces malacceanus. That is generally recognized as safe and non-GMO and resistant several stress accumulated during fermentation and applicable for utilizing cellulosic biomass. This yeast compared to Saccharomyces cerevisiae, some tolerance and using various sugars, including xylose. In addition, this yeast show the high growth rate even at high temperature and efficient protein productivity. So we completed genomes 2015. And found the many the hexose pentose transporters as we expected, including the xylose. And also we found the 30 genes shared with the some-tolerant Hansenella polymorpha, but not shared with some sensitive Culebromyces lactis. So these genes may be required for survival at high temperature. Also, we found the different metabolic flow at 30 and 45 degrees Celsius in this yeast. And this shows the dissolved oxygen levels. You can see the different. This is 30 and this is 45 degrees Celsius. Consistently, the NADH oxidase activity is high at 45 degrees Celsius. And as we expected, high temperatures, cellular or mitochondrial ROS, this is reactive oxygen species level, higher than the 30 degrees Celsius. And the glutathione levels lower at 45 degrees Celsius. And interestingly, NADPH levels were higher at 45 degrees Celsius. And also, we notice the mitochondria morphology is different between 30 and 45 degrees Celsius. At 30 degrees, you can see fusion form, but the 45 show the fission form. To understand the further metabolic change, we try the transcriptome analysis. We incubate cells at 30 degrees Celsius for 4 hours and then shift up to 45 and the further incubate 30 minutes for 2 hours and the isolate RNA and subject it to RNA-seq. So this shows the some of the data, the glycolysis pathway and pentose phosphate pathway. After immediately the temperature up shift, the expressions were reduced. You can see in the glycolysis pathway, but the pentose phosphate pathway, for example, ZWF, nearly constant. And especially the FBP1, this is needed for gluconeogenesis increase. So, looks like the glycolysis is down-regulated and pentose is nearly constant, and then maybe the cycling this pathway. And also, we confirm this transcriptome analysis by the enzyme analysis, and nearly consistent data was obtained from the enzyme activities. So we think this pentose pathway is main pathway at high temperature and then produce NADPH. So this is consistent with our previous data. At high temperatures, NADPH levels higher, and the this is like models. The high temperatures pentose pathway, like cyclic pathway, produce NADPH and remove ROS, which is accumulated at high temperature. So, however, we needed the Culebromyces marxishanus wild type to improve the more resistant to various stresses and also improve the utilization ability of cellulosic biomass. This shows the the earlier obtained mutant, robust mutant, which were isolated under various stresses. So there are two mutants, KMR1042 and 118, both show the resistant at higher temperature, you can see, compared to wild type, and also resistant to the high concentration of glucose and the high ethanol and also hydrogen peroxide. So liquid culture also show the temperature resistant compared to wild type. But in addition, these two mutants show the stronger sedimentation, which is beneficial for the recovery of the cells for next fermentation. Recently, we developed the laboratory adaptation technologies, which is very simple and very efficient the procedure. We call the RLCGT. This method, this is repetitive long-term cultivations with gradual increase of the temperature. So we tested 10 tubes and then obtained the 4 mutant. So very efficient. And obtained mutants show the resistant, the acetic acid and then low pH and also the ethanols and the fluorophore, hydroxymethyl fluorophore. We also, this mutant, actually we obtained the 4 mutant, and that show the higher fermentation abilities. You can see here the wild type is stop the fermentation here, but the mutant use glucose mostly at 40 and 42 degree when we use 16% glucose, and the produce ethanol higher than the wild type. We use this technology for improvement other yeast. This is Candida tropicalis. In this case, we tried the 4 tubes and obtained 1 mutant. This also shows robust mutant phenotype. So the resistant to high glucose, high ethanols, fluorophore, and hydroxymethyl fluorophore resistance. And also, this strain can use xylose. So compared to wild type, the mutant show the use more glucose and produce more ethanols, and also produce ethanol from the xylose. As you know, when we utilize the cellulosic biomass, we need expensive cellulases. So there are 3 typical, the main cellulases, like cerobiohydrolase and glucanase beta glucosidase. Especially this beta glucosidase degrade cerobiotes. So Trichoderma rhizae, this is well known, the cellulose producing fungi, but this fungi produce less the beta glucosidase. So the commercialized cellulases actually mix with the Trichoderma rhizae enzymes and other enzymes, like aspergillus. So if we can make this beta glucosidase by the yeast, we can make the easy or economical ethanol. So we try to mutagenize the Chloromyces to obtain the cerobiose fermenting mutant, because we know the putative genes in these genomes. So we tried 15 times UV treatment, and then finally obtained the cerobiose fermenting mutant, and especially from the SY13. After that, we screened the mutant with 2-deoxyglucose as a glucose analog. You can see cerobiose utilizations, actually assimilation increase here, and then produce ethanol. But unfortunately, glucose assimilation is reduced. So we analyzed the genomes and compare to this mutant, and then 13 to 14s very enhanced the cerobiose assimilation ability. So we found the 4 glucose transporter, 3 the glucose transporter. These mutations maybe stop the glucose, and then stop the glucose repressions, and then produce the beta glucosidase. So we try to do the co-culture of Ku3142. This is the water type, which can utilize glucose, and SY152. This cannot use glucose, but can use cerebios in the glucose and cerebios mediums. You can see the can use glucose cerebios and then produce the ethanols. So now we can do the economic conversion of the cellulosic biomass to ethanols using the Proberomyces wild type, the mutant strains, and T. rizae from the glucose to ethanol. So if we consider the reductions of carbon dioxide emission to produce ethanol, in Japan we have only the household or corporate waste or food loss as raw material. And also we should consider the equipment and also transportation of raw materials and then product. And we needed the further innovative technologies. For such a purpose, we tested the pilot, semi-pilot by two the project. One of the project that is Asia Joint Research Project. The member is Indonesia, Thai, Laos, Japan. We are supported by the district dicty and then convert biomass in Asia to bioethanol, acetate, lactate. So this shows the general ethanol production process, but especially second generation biomass, the cellulose cost is about 40% of the total cost. So we needed the new technologies. So this shows the new technology for bioethanol production. So at high temperature, we can do fermentation, distillation together under low pressure. And after simple distillations, we can further concentrate it by membrane separation. The ethanol we can use into the car after conversion to hydrogen. And also, we developed the direct conversions, very low concentration ethanol to hydrogen to electricity. So this is a recent our project with a Japanese company, and this is a low carbon technology research and development. RE100 distributed power supply utilizing food processing waste. So the food waste from the Nissin holding, and then we try the high temperature fermentation here. And then some is go to membrane separation, and then make the high concentrated ethanol for starters of the engines. And meanwhile, the ethanol low concentrations go to the engines and then the converted hydrogens and then electricity. So this is our centers. We have the three groups and the focusing on some tolerant microbial resources. If you have some interest, please come to do some collaborative work. So this is acknowledgement. Okay, thank you for your attention.
Okay, thank you very much, Professor Mamoru Yamada, for delivering interesting talk. Okay, I would like to move the last keynote speaker. The last speaker is Dr. Mingming Zhu from Cranfield University, UK. Dr. Mingming Zhu, are you there? Hello.
Yes,
Okay.
yes, I am
Sorry,
here.
I think it's too early for you, right? Around 5 p.m.
That's okay.
Okay. I hope
It
you're
is
still
too
awake.
early. It is 5 o'clock in the morning.
Yeah, 5 o'clock. I hope
No,
you're still awake. Okay. Dr. Mingming Zhu, I would like to read your curriculum vitae. Dr. Mingming Zhu is senior lecturer in chemical engineering at Cranfield University, United Kingdom, and adjunct research fellow at the University of Western Australia. He obtained his bachelor degree in mechanical engineering, University of Science and Technology, Beijing, China, and he continued master degree in mechanical and thermal engineering in Tsinghua University, China. I'm sorry if I mistake in reading Chinese. And he obtained his PhD degree in chemical processing and thermal engineering, the University of Western Australia. His expertise advanced combustion and thermochemical processing for low carbon fuels and renewable energy, renewable hydrogen and ammonia technologies, combustion and science technology, catalysis and fuel processing. He published 110 scientific papers indexed by Scopus with HI index of 24. So for Dr. Mingming Zhu, please deliver your talk.
Thank you. I'm going to share my screen. So, are you able to see my screen?
Yes. Is it clear?
Okay. Good morning. Thank you for the invitation to give the talk, and in particular, I would like to thank Hendrix, Yusun, and Maria, who are my previous colleagues at the University of Western Australia. And of course, I would like to acknowledge my PhD supervisor and master supervisor for their training and support. And I would like to thank all the research founders and industry partners to provide the financial support to do all the research. My topic today is about hydrogen and hydrogen carriers production from biomass and biomass waste. The reason I'm talking about the hydrogen today because the hydrogen is back. This is not the first time to talking about hydrogen as a renewable energy or low carbon fuels. In the last 30 years, in 1970s and late 1990s, there are two waves of hydrogen energy. But that was mainly driven by the economics and energy crisis. However, this year and this time, we are talking about hydrogen as a low carbon fuel or zero carbon fuel to decarbonize our society, simply because are driven by the environmental issues, the climate change. In that sense, it looks like there's no way to go back. And it's going to play a very significant role in our the whole energy mix in the future. And the UK government is very ambitious to drive the hydrogen energy in the last few years and nowadays. It provide like £1 billion, what is called net zero innovation portfolios, and target to reduce almost 80% of CO2 emissions by 2035. And hydrogen is one of the key players in decarbonizing the heat power and, of course, the propulsion thermal in the transport. It is estimated to produce 250 to 460 terawatt hydrogen by 2050. And 50% of the commercial transport is going to be powered by hydrogen, particularly in the jet fuels. For example, you convert
you can use liquid hydrogen, or you convert hydrogen to sustainable aviation fuels. Most importantly, according to the recent report, what they want to use hydrogen is from different resources. At the moment, is mainly from methane steam reforming, and of course, the water electrolysis is going to play a significant role now, and it's flying. But it is estimated about still like 20 to 45% of the hydrogen is going to from the biomass. And of course, here biomass is not the current biomass or agriculture waste. The biomass we're talking about is the energy plant. Of course, what we have, the agriculture waste, the food waste, any waste can be used for the hydrogen production, but the feedstock is not sufficiently to produce that enough hydrogen. So I just give you the overview of different hydrogen production and the cost in the current market. In the current commercially available technology for hydrogen is mainly the steam methane reforming. Basically, is the steam reacted with methane. This is widely used in the hydrogen production for the oil refining and use hydrogen for ammonia production. And this is quite cheap, but recently, because of the high price of methane, and also, we achieve the process produce carbon dioxide. And if we want to capture the carbon dioxide, and the cost will goes up. And that's why the levelized cost of hydrogen production now is around, £250. And of course, I believe it's going to be high because this figure is from 2019, and particularly because of the Ukraine and the Russia war, and the price of methane goes up, and in the Europe, and the price of hydrogen production, of course, will goes up as well. And then we're talking about the water electrolysis, and because of the low scale and the high cost of the renewable electricity, the production cost of hydrogen is much higher than the current methane forming. And the people try to use, try to modify the current methane reforming process. For example, you can burn some of the methane to provide the heat for the process. What we call is autothermal reforming process. And of course, we are working on using the calcium to capture the CO2 simultaneously during the steam reforming, which I'm going to give you a very detailed description of the whole process. And we try to reduce the cost. And of course, in a biomass gasification, pyrolysis for the hydrogen productions, and with the carbon CO2 capture, so is another way to produce hydrogen, and the cost is very competitive to the methane reforming process. And of course, in the research areas, we're talking about biological ways, we're talking about the photocatalysis produce hydrogen, but the technology readiness level is still low and in the research discovery stage, and the cost, of course, is very high at the moment. So I'm going to give you a brief overview of a few technology we are developing at Cranfield University and some of the technologies I was involved. So one of the projects we are working on is called HYPER, is a hydrogen production from methane. Of course, that can be adapted to use the biomass waste. So this is supported by the Department of Business, Energy and Industry Strategy in the UK. So the whole process is about to integrate the steam reforming with the carbon capture. Conventionally, and you have steam reforming to produce hydrogen and the carbon dioxide. Afterwards, and after treatment, you use calcium to capture the carbon dioxide. But in this process, we integrate the two processes together. Basically, you put calcium, the lime, into the reactor with the steam and water together. And during the steam reforming process, and the CO2 formed is going to be captured by the lime and turn lime into the limestone. And with the limestone passing through the, passing the cyclone here, and the hydrogen will be separated, and the limestone, calcium dioxide, will be circulated back and go to another reactor here. And this was heated by the residue off gas, and the limestone, when the limestone is subject to the heat, the CO2 will be released and separated, and the lime will goes back to the process. So basically, the concept of this process is to integrate the conventional methane reforming with the limestone capture process to capture the CO2. So the process is based on the current in the GTI, the hydrogen gasification or steam reforming process. And we just try to add the lime into the system to capture the CO2 simultaneously. So we try to design and construct the 1.5 megawatt pilot plant in the university. And this is the site that we try to build. And it is expected the whole system, if it can be successfully demonstrated, is going to reduce like 50% of the capital cost and to achieve 20% cost of the hydrogen production. So another technology I'm going to talk here is the biomass waste pyrolysis process. So basically, if you have the biomass feedstock and you can process it using like supercritical extractions or sonic chemistry to extract value add products, and then you subject to the heat treatment, what we call is pyrolysis, is in the inert environment and heated up to like 600 degrees C or 700 maximum. Pyrolysis process will produce gas, biochar, and of course you have oil. And the pyrolysis gas here you have carbon monoxide, hydrogen, and of course contains methane and carbon dioxide as well. And after gas cleaning, separation, you can produce hydrogen. And biochar can be used as a soil conditioner, or you can use it as a fuel, and you convert biochar into high-value carbon materials like activated carbon for the solvent. And the pyrolysis oil, you can burn it to provide heat for the pyrolysis process, or you want to refine pyrolysis oil to produce other oil products. So we are working on the pyrolysis process because the pyrolysis is different to the gasification. The gasification would require a very high temperature, basically it's more than 900 degrees C to produce syngas. And that is only economically viable at a very large scale. Okay, but the biomass waste has a nature of it being scattered at a small scale. So pyrolysis is particularly suitable for the small scale the biomass waste production and processing here. So the way to use the pyrolysis gas, what I'm talking about today is hydrogen, but of course you can burn hydrogen or the pyrolysis gas in the gas engines for direct heat and power generation. So that's why the whole concept is you can suit for different applications of hydrogen, bioenergy, and if you're chasing biochar, that's all fine. So this is the pilot scale demonstration is the kiln reactor, which can produce like a 100 kilo of biomass, woody biomass, and to produce syngas. And as you can see, the hydrogen concentration in the syngas in the gas, what we call pyrolysis gas, can be reached like 30 or 40% at a relatively high pyrolysis temperature. And one of the concept here is we try to use biochar because biochar is an in situ product. I will try to use biochar as a catalyst to further cracking the pyrolysis oil and to enhance the pyrolysis gas production, particularly to chasing hydrogen yield and the concentration in the pyrolysis gas. And we have done some lab scale in a fixed bed reactor to use the biochar produced in the process and to further enhance the oil, to process the oil to enhance gas productions. As you can see, overall, the gas production can be improved. In some of the cases, can be doubled in terms of the total yield. So that the previous methane reforming and biomass pyrolysis for hydrogen productions, what we're talking about chasing is hydrogen. However, I have to make it clear here that hydrogen as an energy, as a fuel, has a challenge in the current form, simply because of the hydrogen has a very low volumetric density. And of course, hydrogen is very hard to transport and store. And this, if we want to use hydrogen as a fuel, and we have to think about energy density. So this figure just to give you the indications of different fuels. Conventionally, we have diesel, we have biodiesel, we have petrol, and of course we have jet fuels. And both the volumetric density and the gravimetric density are very high. And if we talk about the hydrogen here, of course, is very clean, but the volumetric density of hydrogen is extremely low. That means for a same size of the tank, you can't hold much, energy. So that's why sometimes the hydrogen at the moment, the most easiest or the reasonable, practically way to use hydrogen is to use a carrier. You convert hydrogen to something. In this case, what we are chasing here is try to use like ammonia and methanol as a hydrogen carrier. You can convert hydrogen into methanol, into ammonia. The reason to use ammonia and methanol as a hydrogen carrier, previous slide, just to give you the energy density, so they are reasonably comparable. It's not high enough compared to the current conventional fuels, but also it has a reasonably volumetric and gravimetric density. Most importantly, both ammonia and methanol, they're already in the large production and commercially available. They enjoy the very success and mature infrastructure, and they can be easily stored as a liquid fuels. For example, ammonia, you simply compress ammonia to like 9 bar and at atmospheric temperature, so it will be a liquid. Methanol is already liquid anyway. So it's a very easy store and transport, and they relatively have the high hydrogen concentration, and ammonia has like 17.6 hydrogen wet percentage, and methanol is a little bit lower, but still reasonably high. So, for example, the pyrolysis technology I just mentioned before, you have the biomass go through the pyrolysis process, and you have using the biochar as a catalyst to further cracking the tar pyrolysis oil to produce syngas, and the syngas after cleaning, and you produce hydrogen carbon monoxide. As I said, hydrogen is hard to use, and then you can add a methanol synthesis process to convert hydrogen to methanol, and methanol can be easily transported into wherever it's needed. So this is the concept that we are working on. For the methanol, so of course the current methanol production, you have copper, zinc, aluminum oxide as catalyst, and you can produce different concentrations of copper and zinc in the process, try to tune the compositions of the catalyst to suit different applications, particularly for the biomass pyrolysis, simply because biomass in terms of the concentration varies significantly from one location to another location. That's why we need a catalyst to be robust to handle pyrolysis gas with varying compositions. So these are the pilot plant that we are working on. You have the kiln reactor to build the pyrolysis, and you have the bomb. In this case, we are working on the woody biomass, and you shred it into all biomass powders and put it into the kiln reactor and to produce syngas and add a methanol production plant there. The same value process for ammonia as well. So for ammonia, of course, you can use biomass or waste. At the moment, you can use natural aniline feedstock, and you go through the pyrolysis gasification reforming process to produce hydrogen, and the hydrogen react with nitrogen from air to produce ammonia. At the moment, ammonia is the largest fertilizer feedstock in the agriculture, and what we are trying to do is, can we use ammonia as a fuel, a hydrogen storage transport fuel? So in Japan, for example, they are very ambitious to use ammonia as a fuel. They already demonstrate ammonia in the gas turbines. And in Australia, they try to develop ammonia energy. Basically, they have abundant solar energy, and they use solar panels to produce hydrogen and convert hydrogen to ammonia. Then they ship ammonia to China, Japan, Korea, India. And when they receive it, they can directly use ammonia as a fuel or convert ammonia back to hydrogen to use it. So what we have done before is we tried to use ammonia as a fuel, and we studied the basic combustion characteristics of ammonia and the NOx formation. The use of ammonia has a challenge here is it burns very slow compared to methane. The flame speed of ammonia is only 1/5 of that methane. That's why it's very hard to burn. And also, ammonia contains nitrogen. So during the combustion process, it may form NOx. And that's why the technology development now is trying to increase the burning velocity. Basically, is to make the burning more effective, and of course, simultaneously try to reduce the NOx emission. And of course, you can directly use ammonia as a fuel cell, like hydrogen fuel cell in the solid oxide fuel cell, the high temperature solid oxide, to directly convert ammonia to electricity. So there are lots of research is going on in the worldwide in try to use ammonia as a fuel. So this is just to give examples of what we are doing here. In a nutshell, so hydrogen is very, very active in the UK, I believe, in the world as well. At Cranfield University, for those who don't know, we don't have an undergraduate. We only the postgraduate focused and working closely with the industry, and particularly is the #1 in the aerospace in the Europe. Even in the world, in the campus we have the runaway, So we have been very, actively in driving the hydrogen energy. We produce hydrogen from renewable electrolysis process, and we store and compress hydrogen, and we use the hydrogen as a liquid fuel in the jet engines. And we convert hydrogen to ammonia. We use ammonia in the internal combustion engines, jet engines, and lots of activities going on at the moment. So thank you. That is my talk today. So I would like to answer any questions. Thank you.
Okay. Thank you very much, Dr. Miming, for your nice talk. So from now, I would like to open for discussion. We have around 20 minutes for discussions. Do you have any questions? Okay, please. Dr. Weni. Please wait for a moment.
Okay, thank you very much, Dr. Collis, as the chairman. Thank you for the chance. I would like to, to ask to Pak Bambang. Yeah, Pak Bambang. Okay, I apologize because I missed out your talk. Maybe I only can see the first slide, maybe. But what I would like to ask is about the supercritical. You mentioned about supercritical liquid extraction. So because I'm doing I'm teaching about the aroma technology and also the like essential oil extraction as well as something extracted from aromatic plants. I just would like to ask whether there is any limitation or challenge in the application for extracting aroma or flavor using the advanced technology that you have explained. Is there any, something that limit the application? Maybe is it only for plants, or maybe the kind of materials that can be used? I think that's the first question. And then the second one is there any closest facilities in Indonesia, especially that is accessible for us to do this? Because as I know, maybe here we don't have that facilities at the moment. And if not, is there any possibility for us to build one? Yeah, I mean, because this will be important to support many research and in collaboration in the future. Thank you.
Okay, Dr. Bambang, Professor Bambang. Yeah.
Okay, thank you for your question. I would like to answer the last question. For the this year, we have a research project for building the supercritical fluid extraction, and maybe until now 50%, and we can try to extract some of the biomass material. For example, we will extract the citron letters and then gingers and extra. For the supercritical fluid extraction, the important is to determine the optimal process. I mean that temperature and pressure, because every material, has the specific optimal condition for supercritical fluid. Okay.
So it means, is there any limitation for samples? Like what kind of sample that can be extracted by supercritical?
Yeah, this is the topic of research, because we can use the carbon dioxide and then methanol extra. It depends the material. So in the research of the supercritical fluid it is specific. Every material will be extracted. Use the certain solvent and certain temperature and pressure. So,
yeah, so it depends on the biomass that we want to extract,
Yeah.
right? So the solvent and also the condition, like temperature, pressure, also it depends on the sample. How about Pueni? Is it answer your question?
Thank you. So it should be optimized by, depend on the
Depend
need
on
of the research. And then about the second question, so
the closest place.
The closest place, maybe
the closest place for doing supercritical extraction.
or LIPI
or in Brawijaya
around
University.
here.
Yeah.
Do we have any
I have
Brawijaya?
a project for this year
Yes.
for making the system for supercritical fluid extraction. If you want to cooperate with me,
Okay, sure, thank you.
Yeah, I think because Buweni, Dr.
In
Weni is
Brawijaya maybe,
focus on aroma compound like essential oil.
Yes, and also the flavor, maybe for extraction, you know,
I think
especially the
it will
the
be
aroma.
good collaboration between
Okay,
Buweni
thank you.
and Pak Bambang.
Thank you. Because if there is no facilities at the moment in the university, so it might be important or useful in the future, Pak Bambang, to have the
I
kind
construct
of
myself.
instrument.
I myself with my team.
Here, okay. Thank you, Pak Bambang.
Yes, thank you, Dr. Weni and Prof. Bambang. Is there any other question? Okay, I will read a question from Zoom. The question from Dr. Johnny to Professor Yamada. Professor Yamada, are you still there?
Yes, I'm here.
Okay, thank you for us. The question is, thermotolerant yeast have some advantages to produce ethanol through fermentation. But if I'm not wrong, biofuel production has been constrained by the fact that heat and ethanol itself can be deadly or damaging the yeast at high levels. What is your experience dealing with this fact? Can you catch the question?
I understand these questions. Even Saccharomyces cerevisiae that also has the critical concentration of ethanol. So ethanol also make some negative effect on the yeast itself. But our case, we can produce more than the 8 or 9%. That is okay. And also our system to convert the ethanol to hydrogen, the ethanol concentrations we use like 7%. Or maybe a little bit lower than 7% is okay. So for our system, maybe no problem. It's okay. This is the answer.
Okay, thank you for your answer. Another question to Prof. Yamada also from Dr. Dimas. In the case of Candida tropicalis X17, to obtain some of the mutants, you did only temperature adaptation to the wild type, but some results show that the mutant also demonstrate resistance to other chemical that may be act as stressor to the strain. Can you give the explanation in detail about this phenomena? What is the relation?
So this new method, that is, we try to increase the temperature gradually during the fermentation process. In the beginning, and also we incubate like 1 week. So in the beginning there are nutrients, but after that nutrient also limited and also accumulate byproduct. So there are many stress during the cultivation. So that's why we obtain by this method to get the mutant, and the mutants show us the resistance to several stresses. That's answer.
Okay. How about Dr. Dimas? Is it answer your question? I think it's very clear. Eh? Okay. Is there any other question? No. Okay. A question from Mayang, Dr. Mayang, to Dr. Miming Zhu. Would you please share about biomass via dark fermentation or TPAD application to produce hydrogen as biofuel in the UK or Australia as your experience? Can you share?
Yeah. So biomass waste, anaerobic digestion process in the UK is actually, in the Australia is not that many, but it's still developing. And but in the UK, it's very active. It's a very commercial, mature market actually, anaerobic digestion process. For the two-phase anaerobic digestion, as you mentioned, TPAD is try to produce hydrogen in the first phase, and then in the second phase produce methane. It is in the developed stage. Actually, at the Cranfield University, we do have people or researchers working in that space. What they try to do is actually working with the paper and the pulp industry, try to develop that two-phase anaerobic digestion to produce a hydrogen, and use the hydrogen on burning in the internal combustion engines for the on-site use. So that is to convert particular industrial waste to hydrogen and use the hydrogen for the fuel used for heat or power generation. So this is one direction, but actually for many, because it is already commercially operated anaerobic digestion, and many of them actually are chasing is to convert, because anaerobic digestion process produce methane and CO2. So what they are chasing here is try to convert CO2 to methane by the methanation process, and then they can inject the methane into the existing gas fuel, gas grid. So that biomethane is regarded as a low carbon fuel because it's from the biomass and biomass waste that help to reduce the carbon emissions. That's another very active area actually.
Okay. How about the answer? Is it okay? Okay. Another question from Dr. Mayang is, would you please also explain the readiness of facility in applying hydrogen as a fuel in UK or in Australia?
Actually, using hydrogen in the fuel is in early stage. There are different ways to use it. If you burn hydrogen in the internal combustion engines or in the gas turbines, in the university, we have demonstrated that there's no problem. It's a pilot scale demonstration at a university scale because Cranfield University has been very active in the jet engines, aerospace, and we can burn hydrogen successfully to use hydrogen as a fuel. But for the commercial use of hydrogen for small scale gas internal combustion engines, they are blending hydrogen with methane, burning hydrogen in syngas, there's no issue. But pure hydrogen, no, there's no commercial available, commercial available in the market at the moment. We have been working with Airbus and one of the largest, jet engine producer. They are working on using the liquid hydrogen on board and to design the engine at the moment to use liquid hydrogen as a direct fuel. But that is in the development stage, I should say. And also for hydrogen use in the fuel cell is another market. Hydrogen fuel cell at a low temperature basically is proton exchange fuel cell. They are small scale demonstration, basically for stationary power generation. And nowadays, we try to use that fuel cell in the jet engines for the very short distance travel, okay? Not the long distance travel, because you carry the fuel cell is very heavy as well. But there's no large-scale hydrogen fuel cell in the market neither, because of the cost issues. And the development in that fuel cell area is to use the solid oxide fuel cell. Basically, it's a high temperature, and you can handle hydrogen, any purity of hydrogen, because the current commercial fuel cell can only handle hydrogen with purity of 99.99. Basically, it's a very challenge. And the solid oxide fuel cell can handle hydrogen, ammonia, methanol, syngas, any fuel, because it basically is a high temperature burning. But that process is, first of all, is a high temperature costly. The second is, in any transport applications, you go through on, off, on, off, on, off. The dynamic of the system is very challenging for the material, the degradation very quickly. That is another technical challenge. Of course, there's a catalytic reaction catalyst development to improve the efficiency always. That's a few applications of the hydrogen and the current market. I should say it's still in the early stage, but I believe as long as the reason I should say for the hydrogen is not only the use of hydrogen, it's actually the production of the hydrogen to provide sufficient hydrogen for the use. You can produce hydrogen, but store and transport hydrogen to where it is needed and used is a challenge at the moment. So that's why the whole value chain has to be considered when you use hydrogen as a very emerging or low carbon fuels. Thank you.
Okay. So it's also facing by many countries. Yeah, the price is still high, right? To develop the biofuel, the prices are also still high. Okay. How about the audience in this room? Do you have? Okay. Dr. Bambang Susilo.
Okay. Thank you. I have question.
Maybe last question.
Last question, yeah. I deliver to Prof. Su, yeah.
Yeah.
Okay, yeah. Henry Kissinger said that control food and you control the people, and control oil or energy and you control the nations. It means that the energy needs in the world is unlimited. Yeah. So it is a problem about the agricultural land use. It is for food or for energy. Yeah. Could you tell us how about the international policy in relation with the agricultural land use? It is for food or for energy? Thank you.
So the question for me?
for
okay,
Dr. Zhu.
Yeah. I think that is very clear. That is not for energy, agricultural waste can only be used as a byproduct. If you want to produce the waste, to produce energy as a byproduct for the on-site use. As I mentioned, even in the UK, the policy makers, they make it very clear. Even the hydrogen from the biomass or biomass waste for energy plant, it is mainly from the energy plant. It's natural based. Basically, it's what they call is the plant, the energy which grows faster to produce energy, hydrogen, is not competing with the land use for agriculture. They make it very clear.
Okay. Okay, because the time is very limited, already 11:45. We have 3 excellent speakers in this session. One focus on bioethanol production, and one focus on biohydrogen, and Professor Bambang focus on biodiesel, right? So we have 3 different focus for each speaker. And because the time is already run out, so I would like to thank you very much for all speakers that delivered their excellent talk. And I hope you can enjoy the next session in parallel session. Thank you very much. I would like to give to the MC.
Thank you for the wonderful session, Dr. Nurholis. And that, ladies and gentlemen, marks the end of our plenary session. And now we hope that all the sessions would provide a very insightful inspiration to all of you participants of Icgab 2022.
I would like to thank all the keynote speakers for the knowledge and insights.
The moderators for guiding the sessions.
And not to forget, the participants for attending this plenary session. Thus, bring us to the end of the plenary session in the 6th Icgab 2022. We would like to remind the participants to join the parallel session, which will be conducted online at 1 p.m. Western Indonesia time. Please kindly join the room 10 minutes ahead in order to be prepared for the presentations. I, Barik Ilham,
and I, Theodore Rodelia, would like to apologize for any mistakes and mispronunciations in the event. We wish you a very good luck on your presentations and hope to see you again soon. Until then, wassalamualaikum warahmatullahi wabarakatuh. Thank you, everyone.